Hello students, this is example number 4. We're going to throw a slightly different twist to this example. So far, we've simply plugged and played with this equation, right? The most difficult part was a curveball that I might have thrown to you in terms of changing around the units. So most of the difficulty in the previous 3 examples was with unit conversion. In this case, I'm going to turn it around a little bit, and instead of asking you to calculate what the diluted concentration, I'm going to ask you to calculate something different. Specifically, for example number 4, you're being told that on February 29, 2013, the temperature in the Ottawa River is 1 degree Celsius. You're also told that according to the local law in Ottawa, the highest increase in temperature for the Ottawa River is 4 degrees Celsius. That is, regardless of what the existing temperature is, any addition of hotter water can only increase the temperature by 4 degrees Celsius. You're then informed that the concentration of the wastewater from the fictitious nuclear plant in Ottawa that's being dumped in the Ottawa River is 10 degrees Celsius. You're also informed that the flow of the Ottawa River, the flow of the stream, is 1950 cubic meters per second. You're then asked to calculate then, in order to keep the impact from this fictitious nuclear plant to within this maximum increase, what is the maximum flow from the waste? What is the maximum flow of hotter water from the nuclear plant into the Ottawa River? Now, at first glance, it looks like we don't have enough to put into this equation. Do you recognize that what we'll have to do is rearrange this equation to write it in terms of the waste flow equals to? Okay. Now, by looking at this, we have the stream temperature right here. We have the waste temperature right here. We have the stream flow right there and right there. And we're looking for the waste flow. Okay. What about the diluted temperature? Well, we compute the diluted temperature actually based on this information here. We are told that the diluted temperature cannot be any hotter than 4 degrees above the existing temperature. What that implies then is that the diluted temperature is equal to the existing temperature, in our case, on this date, 1 degree Celsius plus 4 degrees Celsius. That means that the diluted temperature is 5 degrees Celsius. With that in mind, we now have this. We can rearrange this formula in terms of waste flow equals to give us the highest waste flow we can get from the fictitious nuclear plant in Ottawa so that we don't go above this maximum temperature increase. Let me show you how. The first step is I'm going to rewrite this whole formula. Then I'm going to plug into it all the information that I have. Voila. Now what I'm going to do is I'm going to do this 2 ways. The first way is I'm going to write down QW equals to. That is, I'm going to skip all the steps and give you the answer, so that if you want to see if you can get the same answer, I'll leave that up to you. The second way then is I'm going to pause and I'm going to go through it step by step. So if you've gone through all the steps, see if you can obtain that the waste flow is equal to 1560 cubic meters per second. Otherwise, if you don't want to give it a try, or if you just want to follow along with me, I'm now going to erase this and do it step by step. The first thing I'm going to do is I'm going to calculate these products wherever I can. So the first thing I did, and the mathematicians in you are going to look at this and say, this is a atrocious form. I apologize, yes. So I've multiplied this out. This I can't multiply out because this is my unknown. This I can't touch. So what I want to do is, with the end goal of having QW on this side of the equal sign and numbers on the other side. So first thing I'm going to do is I'm going to multiply both sides by this denominator. So I'm going to multiply this side by 1950 cubic meters per second plus QW, and I'm going to multiply this side by 1915 cubic meters per second plus QW. The benefit is that it's going to disappear on this side and appear on that side. Now, I get to multiply each one of these values by 5 degrees C. So notice how things are starting to come together, right? We have only a small portion here that has QW in it. Only a small portion in here that has QW in it. These here are just numbers, right? Numbers with units. Don't forget, if I'm multiplying the numbers, then that means I have to multiply the units. That's why the units look like this. Okay? So, if I can take this and bring it to this side, and I can take this with QW and bring it to that side, I'm that much closer to solving it for QW. Let's do it. Okay, so you see what I did? I took this and brought it to this side. That's why it has a negative sign. I took this and brought it to this side, and that's why it has a negative sign. So now, what I have, I'm just going to work this out. So minus 10 degrees Celsius QW plus 5 degrees Celsius QW is So now, I'm going to divide both sides by minus 5 degrees Celsius. And do you see what happens? Minus 5 degrees Celsius and minus 5 degrees Celsius cancels out. You're only left with QW on this side. Degrees Celsius and degrees Celsius cancels out. The minus and the minus cancels out. You're only left with cubic meters per second on this side. When you do 7,800 divided by 5, you actually get so that the final answer is 1560 cubic meters per second. I'm not going to turn this into an obvious final answer so it's unmistakable. Therefore, then I'm going to put an amazing cloud next to it, a giant chevron or arrow pointing to it. Voila. So what we calculated here then was the highest flow of the hotter wastewater from the fictitious nuclear plant that can be dumped into the Ottawa River so that we keep the increase in temperature in the Ottawa River to no more than 4 degrees Celsius. This is a slightly closer application to a real-life scenario. Thank you for your time.